morning general chemistry. We are picking up with our part 3 of our notes in chapter 19, talking about neutralization of reactions today. So we've talked about strong acids and bases, we've talked about the pH scale, and you're doing a project right now where you should be looking at a reaction between an acid and a base. Those reactions we call neutralization reactions. So let's define it. Acid-base reactions where our hydronium, that's H3O plus, and hydroxide, OH negative, create water and a neutral salt. So here's an example of that. Remember, we can tell it's an acid because it's got an H in front. So it's nitric acid and sodium hydroxide. Notice it has hydroxide actually in the formula. Create sodium nitrate, which is a neutral salt, so it's not an acid or a base, and water. Few things about these types of reactions. The neutralization reactions result in a pH of 7. So if it's if you do the same ratio of acids to base based on their chemical equation, you should get a neutral pH. And we can tell if it's neutral using our indicator, so universal indicator or a pH indicator. Some neutralization reactions don't form neutral solutions because of the concentration of hydronium and hydroxide. So if you have a higher amount of hydronium or a higher amount of hydroxide, obviously that solution is not going to be fully neutralized. Okay, question for you. If you spill a strong acid and try to neutralize it with a weak base, the resulting solution is still acidic. Why? So remember what a strong acid is and a weak base would be. Strong acids completely ionize, while a weak base don't completely ionize. So if you mix these two together, we have higher concentrations of hydronium or H plus ions in solution than we do hydroxide ions in solution. Overall, that would mean it would be more acidic. All right, so let's talk about the self-ionization of water and pH. Now we know that water has a pH of 7, but you may or may not have noticed water starts with an H, so we might think it's an acid, and you wouldn't be wrong. So water is actually the most common acid and the most common base because it does what we call self-ionization. And by ionization, again, we mean it breaks into its ions. This occurs to a small extent between the molecules of the water. So water molecules are bumping into each other when they're in liquid form. Some of them will give up that hydrogen and will end up with hydronium and some hydroxides to a small extent. And they can go back and forth. So even though this reaction is happening, water still acts as neutral because the concentration, that's what these brackets mean, concentration of hydroxide and the concentration of hydronium are equal. Okay, again, brackets mean concentration. Here's an example. You can visualize what these particles would look like. We have two water molecules. They'd be bumping into each other. One gives up that hydrogen so that we have an oxygen bonded with 3 hydrogen and then a hydrogen bonded with one oxygen. Okay, this would have a +1 charge. This would have a negative charge. So this results in an ionization constant for water. Neutral solutions are aqueous solutions where acid solutions is 1. Their hydronium ions are going to be a higher concentration than a hydroxide ion. And the alkaline, which is another word for a base solution, is 1 where the hydronium is less than the concentration of the hydroxide ion. So that's how we can really define acid solutions and alkaline solutions. All right, that's it for today. We'll see you in class.